Section 3.5 deals with continuity and end behavior. So let's look at a few examples from section 3.5. In the first part of the exercises, they're asking you to determine whether each function is continuous at the given x value and justify your answer using the continuity test. So, in this first example, problem 13, we're given this function y equals x plus 1 over x minus 2 and an x value equal to 2. Well, if you plug 2 into this function for x, your numerator is 2 plus 1, which is 3. Your denominator is 2 minus 2, which is 0. And a denominator of 0 is undefined. So in this case, it is discontinuous or not continuous. And the justification for that is because this x value is not in the domain of the function, meaning that it's not one of the numbers that you can plug into the function. Okay, number 16. Similar instructions. We're finding out whether or not this is continuous. In this case, we have what's called a piecewise defined function, which means that for some of your values, you plug the numbers into this part, and for some of the x values, you plug your numbers into this part. Well, if you were to make a graph of this, and this is not necessarily part of what you would have to do in order to do the problem, but what you would see is that this part of the function going all the way up to an x value of -4 will end up giving you a y value that gets up to -7. 3, 4, 5, 6, 7. And so you would have a piece of your graph that looks like this, whereas over here, when you plug in values that are greater than -4, then what you'll end up with is y values that get almost up to +6. And you end up with the other piece of your graph looking like this. So you can see by the graph that it's discontinuous. Well, how do you show that though? Well, in this particular case, what you can do is make a t-chart and plug in some x values into each piece that are getting progressively closer to the x value that you're interested in. So I wouldn't recommend doing a graph on this problem. I would recommend doing t-charts. So if I'm plugging numbers into the first piece, I have to plug in numbers that are less than -4. So maybe I would do -5 and maybe -4.5 and maybe -4.1 and see what those numbers approach. Well, if I plug in -5, I've got -15 plus 5, which is -10. If I plug in -4.5, then what I would have is -13.5 plus 5, which is -8.5. And if I plug in -4.1, then I have -12.3 plus 5, which is -7.3. I don't know. I think so. I should have done this one ahead of time, I guess. But you can see that it's approaching this y value that we had over here of -7. And if you wanted to get really close, you could even do things like -4.01, which should give you something like -7.03. All right, but what about on the other side of this function? Well, we need to plug in numbers that are larger than -4. So for example, you could start with something like -3. Well, if you plug in -3, the opposite of -3 is +3, plus 2 is 5. But then if you want, well, not if you want, but you need to get closer and closer to that -4. So maybe try like -3.5. Well, making that the opposite of -3.5 is +3.5 plus 2 is 5.5. And you could do -3.1. When you plug that in, you get +5.1, and so on. So you're getting closer and closer to +5. So in this case, as you come toward an x value of -4 from the left-hand side of your graph, you're approaching a different number than what you get as you approach from the right-hand side of your graph. Therefore, it is discontinuous. All right, Also, problem number 12. Let's go ahead and look at that one. Well, in this case, you can plug 1 into the function, no problem at all. 1 to the third is 1, minus 4, so you end up with a negative 3 as a value. So it's not a domain issue like number 13. And in this case, we want to see what's going to happen as we approach 1 from the left and from the right. Does it approach the same number or not? Okay, so on one side I want to approach from the left, so I want to use numbers that are smaller than 1. For example, 0.9, 0.99, and 0.999 are all smaller than 1, but get closer to 1 as you go. And then on the right side, we want things that are larger than 1. So for example, 1.1, 1.01, and 1.001. All right, in this case, if you were to take 0.9 and raise it to the third power, what would you get? Well, you would get 0.729, and then subtract 4 from that result, and you get negative 3.271. All right, so then if you plug in 0.99 into this function and raise it to the third power and then subtract 4, I'm just going to round to 3 decimal places here, you would get negative 3.030. Finally, we also want to see what happens when we plug in 0.999 into this function, which means raising it to the third power and then subtracting 4. And here we get negative 3.003. So it looks like these values are approaching negative 3. Let's see what happens on this side. If I take 1.1 raised to the third power and then subtract 4, I get negative 2.669. 1.01 raised to the third power and then subtract 4, I get negative 2.970 if I'm rounding to 3 decimal places. And then 1.001 raised to the third power and then subtract 4, I get negative 2.997. So it looks like these are also approaching negative 3 for their y value. So in this particular case, it appears that the function is continuous at a value of x equal to 1. And in fact, this particular function is a polynomial. So polynomials are continuous everywhere that they're defined.